So what I'd like to talk about is implementing the type system of Vojevodsky in his paper, Universe Polymorphic Type System. We're trying to. And so at an early stage, I decided to implement it in OCaml, since that's what Coq is written in. And why did I decide to implement it? Well, the idea was to have a prototype that would serve as a test bed to decide whether it was feasible to write a proof assistant that would be based on this type theory. It's, at its core, it'll be rather different from the type theory or type system that's in Coq, because definitional equality is not decidable, and so occasionally you'll have to ask the user to prove one. And for the same reason, when shipping the proof to a distant site to be verified, independently, you'll have to ship the proofs of the definitional equalities with. And so Vojevodsky's suggestion was to ship the entire derivation tree. So what I wanted to do was to implement it, and I started writing code in OCaml, and I started writing some routines that would do type checking in TS. And then at a certain point, I started thinking, well, I really have to start thinking about creating those derivation trees that we're going to ship off to distant sites. But I didn't want to have the knowledge of the inference rules encoded just in OCaml code. I wanted them to be machine readable and to be able to ship them off too, along with the derivation tree. And so I started thinking about a syntax for encoding inference rules, and got completely confused after 2 days of puzzlement. And I'll show you exactly where I got puzzled. And then Andre noticed my confusion and said I should really look into logical frameworks. Is it singular or plural? Singular. Is it the logical framework or a logical framework? All right. All right, so there are various ones. And so I asked Dan Licata and Bob Harper about it by email, and the very next day they gave me a 2-hour tutorial about their particular logical framework, which is incorporated into 12th. And I just thought it was the coolest thing ever, because it seemed to solve all of my notational problems for encoding the inference rules, and it meant in particular my encoding of the inference rules didn't have to talk about substitution of variables or about contexts or about binding of variables. The only change in point of view that occurred then was that the standalone proof checker would have to incorporate some type checking for LF, but that's rather simple to write. That can be done in under 500 lines. So that was a real revelation. And then once I had that revelation from Bob and Dan, the code just wrote itself, and I've been coding nonstop every hour since then. About 5 weeks ago or 4 weeks ago, whatever it was. Well, the problem is I wake up at 3 in the morning thinking of the latest bug or feature and have an idea, and then, well, I better go put it in, and so I do. So I thought it might be illuminating. Maybe a lot of people are experts here on various logical frameworks, so they maybe have gone through this path themselves. But so for people who are not, and maybe for our distant viewers who are not, maybe they can learn something about what a logical framework is and why it's useful. And I think they're under-advertised, because I had never heard of them before, paid attention to them. And so anyway, I'll tell you a little bit about the background, and then about the implementation, and then show you some of the code and some of the files and have a tiny demo, and we'll see how that goes. So the type system TFs by Voevodsky. Do you say a type system or a type theory? Or is type theory the general subject? All right, so it's a type system. But other people have said a type theory?
Yeah, I would use those two.
All right. All right, thank you for the clarification. So it has some expressions of three sorts. Universal level expressions, type expressions, and object expressions. And the what you might write in Coq as pi x colon a comma b gets encoded in his syntax as pi semicolon x a b. So he thinks of everything as a tree where the branches of the tree are all expressions, and any bound variables get put in to the label on the head of the tree. So this is the label on the head, and those are the two branches. And implicitly what's happening here is that x is bound in B, and this is a type. So this will be a T expression. And if A and B are well formed, this will turn out to be a type, potentially. So that's the idea. And then what you might write as lambda gets encoded similarly. You have two branches this time, the type and the body of the lambda expression. And then you put the name of the variable in there. And again, x is bound in B. And that's going to be an O expression. Oh, yeah, thank you. And then if everything types out well, this will turn out to have type capital B with the this will turn out to have oh yeah, this will turn out to have type this type. And then let's just do one more example. There are many. Well, let's just do function application. So this will be an O expression, and this he encodes as with the label EV for evaluation. And then you put the three things inside of there, but you also put the type of the result inside of there. So here, F and Z are supposed to be O expressions. And then the B is a T expression. Oh, and I could have said that up here also, that these things are both supposed to be T expressions. That's a T expression. That's an O expression. And then the X is bound in B. And that gives the type of the answer. So the type might turn out to be B with the Z replacing X. So again, this obeys the same rules. It's got three sub-expressions, linearly ordered, and they're expressions of either of O type, T type, or U type, and the syntax specifies which type it's supposed to be. And then the U expressions are involved with universe handling. And then there are 4 basic types of judgment. T is a type. O is of type T. 2 types are equal. And two objects are equal. And then there's some inference rules. And there seem to be 38 or more inference rules. And so, for example, there's this one that you can think of as casting to another type. And then let me just write down one more. I'll just write down beta reduction, because that's the one that got me confused about how to encode it. I'm going to go to the board below for the sake of the camera.
So why here is just an arbitrary co-expression? Like,
Yeah.
supposed to give her
Well, yeah, that's why it's to the right of the judgment.
yeah,
So it's the usual convention. The variables go to the left. And I could have made these 2 variables different for clarity's sake. And then the other thing that was confusing about the presentation of TS. Yeah. Yeah, so that's right. So all the things that appear to the left of colons are supposed to be O expressions. Those are the objects. And all the things to the right of colons are supposed to be T expressions. Those are going to be the types. There's an EL operator that goes from the O expression that names the universe to the type that is the universe. So it's Tarski style. U expressions are things like 0, 1, 2, 3, or a universe level variable, or things like variable plus 1, variable plus 2, or a maximum of 2 expressions. Yeah, there are some more judgments having to do with universe expressions. Yeah, like you might say universe variable number 1 is less than universe variable number 2. Or maybe you put a maximum in. And then, we heard from Matthew about how Coq handles universes. The difference in TS is that the universe equations and inequalities can have arbitrary expressions on both sides. And his hope is that a proof assistant will not be generating new universe variables all the time, and so you won't have to make them go away later. And not very many will be introduced at all, and maybe checking won't be very hard. But that has yet to be explored.
What does U1 less than U2 mean?
Well, that might be 4, and that might be 6, and so it would mean the usual thing, except they're variables. And so what it really means is, can you satisfy all of the constraints on all of the universe variables by plugging in natural numbers? So it appears to me that that's going to have to be that'll be left to the well, our distant validator might be shipped the natural numbers. That'd probably be the most convenient thing to do. There's no reason for the validator of the proof to have to think about how to satisfy these equations. So, but then also there are definitions. So for example, you might want to define something. And the, I've already mentioned that the lambdas, the bound variable here is a variable that stands for an O expression. So we don't have lambdas that take types. We don't have lambdas that take universe levels. They're always O expressions. On the other hand, the definitions need to take universe levels and types so that things can be properly polymorphic. And so you might have, you might want to define F to be of type pi, U1, and these would be universe levels. And then maybe also some type variables. And then maybe then finally some variables of the traditional sort. And then finally some expression. Yeah, families of types. And so what you would put to the right, what you would put here, in there could go, oh yeah, no, there should go, sorry. Oh yeah, right. So, so there might go some expression, a T expression, which is supposed to be a type. So don't write that word. Or you might have some term there and declare it to be of some type and expect the proof checker to check it for you. And so you're giving a type, and this will be a type family, or you're giving a term and a type, and you're making a definition of a term. And
Apparently the arguments cannot be families of types.
Oh yeah, well, I don't know.
Would you write pi t colon a arrow type?
No, this is the only thing that seems to be allowed in what he's envisioning. Oh yeah, so there's a certain, the way you convert a universe, there's an operator for converting a universe level variable, thought of as a natural number, to the actual type that is it represents. So then you can stick that in there when you call the thing. Oh, yeah, you could. We have names of types. That's a good point. Does that answer your question? Oh, good. All right, good. Then it's all right. So in any case, in Clock, when you type in a definition, it's usually accepted immediately because it just type checks it. But type checking in TS is not going to be decidable, and so definitions might not work. And so after typing this period, the proof assistant might ask you for a proof that your definition is well typed. And so the proof you're going to have to provide. And I'll show you how that's provided. So, so anyway, what I spent 2 days thinking about was how to encode this stuff in syntax. And I came up with some sort of syntax for this, but the contexts were still there, and I sort of had the idea that I would have variables representing judgments, and it would be some sort of a term of some sort that would prove that the judgment was okay. And I would do that, the same thing down here too. And then I would be able to describe the inference rule as some sort of pi type that was occupied by means of an axiom. And but then I just got really frustrated down here because of these substitutions and the problem of having to mention these variables explicitly just made me really sad. So I threw it away and got puzzled, and that's when I learned about LF. And so what happens in LF, briefly, is that there's an embedding of the type theory that you're studying into a different type theory, which is decidable. And the idea is, well, let's call this phi. Does everybody, do I have to say what the syntax of LF is? Let me just say briefly. So in the syntax of LF, there are objects, and there are types or type families. And there are kinds. And objects belong to types, which are some of the type families. And type families belong to kinds. And a typical expression for an atomic object would be taking a constant or a variable and applying it to a bunch of objects. Call that type R. And then the other type of object, which is implicit in this notation, is the canonical object, and that involves lambdas. Oh, and then it's just an R, because I put all the lambdas in. And then for type families, there are constants, B, and then you can form them in two ways. You can apply one of these constants to a bunch of terms, or you can have a dependent type. And then for kinds, there are very few sorts of kinds. They have to accept a number of type arguments and then return the most basic kind, which is called type. And then Tn minus, oh yeah, that's right. And so type families, so if this is a kind, then one of these type forming constants would have a kind of its own, and then also these constants here would have types. All right, so that briefly is what that's about. And so to embed TS in LF, you have to introduce a new type family constant. So I chose U expression, T expression, and O expression, and declared them to be of kind type. And then for the four judgments, we have is type. Well, I guess I'm just following what Dan did for us in the example where he started coding this up in 12. So this is really what Dan Licata showed us. So T expression goes to type has type, takes an O expression and a T expression, and that's it. Then you have a type, which may or may not be occupied. And then type equality takes two T expressions. And then object equality takes two O expressions and a type expression and gives you a new type. And then, so these are the type family constants. And then we have the object family, the object constants. The object constants correspond to the names of the labels.
This is what I would call synthetic information.
So we've seen three names of labels. We take the names of the variables out, since TF handles that for us. And we introduce these things. So pi is supposed to take a type, and a type that depends on a variable that could be an O expression. So takes a T expression and a T expression that depends on a variable, and it gives you a T expression. And F takes an O expression and an O expression and again a T expression that depends on a variable, and it gives you an O expression. And lambda takes a T expression and an O expression that depends on an O expression, a variable in other words, and gives you an O expression. And then the way you define the embedding phi is simple. Suppose you have one of these things in Voevodsky's notation. Then what you do is, first of all, you remove the variable from the label, and you stick it on the sub-expression where the variable is bound. And let me use this brief notation for lambda in TF. Yeah, it's very confusing. Pardon? What? I didn't hear the question. Oh yeah, this is an LF lambda. Oh, it will be. It's about to be. For now, it's just notation in my brain. Now we're trying to... Yeah, so now here's the final story in LF. So now this is not yet LF. So now what we do, you see this is a function. We have to write it in the LF notation. We have to write it with its spaces in between its arguments, right? Yeah, so then we have to put A, and then we have to put, whoops, lambda x comma b. And so now we finally have something in LF notation. We have our brackets? Bracketed pi. Yeah, I put brackets around them just to keep them in another namespace from the namespace the user might use for variables. What? There are brackets here.
Pi, A, then lambda. Lambda doesn't have rounding.
Okay, because that's a different lambda.
Yeah, this is a TF lambda. That's the difference.
Okay.
And the TF lambda is not to be confused with the other lambda. So let's do that other lambda as an example. So here I'm just copying this, and I'm converting the Greek letter into the ASCII thing. And then let's just do this intermediate stage, which I like to do, so that I know where the variable is supposed to go. And then finally, this now becomes a function that gets applied to its two arguments. And now we think of this lambda as being the TF lambda. And so now we have an expression where we have both the TS lambda appearing as an object constant of LTS, TS lambda appearing as an object constant of LF, and then with this other lambda is the lambda of LF. LF, yeah.
What's the difference between the letter lambda of LF and the arrow you
So this is just informal here. So this line is TS. This line is informal. It might have been another way to write down TS. And this is finally LF. Overload it? We should? Well, anyway, that's the translation. So what do you do with contexts? Then the really cool thing is that you have to know is that if you have some expression and you embed it with this translation and it types out inside LF to be of type O expression, then that's going to happen if and only if O is an O expression in the sense of Voevodsky, which means that it's got every node has the right number of subnodes, and they're all classified correctly about whether they're T or O. So it's got the syntax right. So those things encode the syntax. And then what do you do with the context? So we're still going from TS to LF with phi. And then what we do with the context, x:(t), in TS, we send that to x:(tx), comma, let's say I, is type of x. And that takes care of it. No, sorry. Nope. I want to do the type judgment first. So he writes, so suppose you have, I know, let me put this, T being a type. To say that you have a type, you want to say that you have a T expression and that you also have some justification for it, some term of LF justifying that it's a type. And then to say that you have a term of type T, oh yeah, I want it to the right, to the left. Well, it depends on whether you, well, no, I guess, I think what happened here was I started thinking of these things, which are in the definitions. And so I'm thinking of encoding these things. So that's what I was doing. So what happens is that when I encode a definition, I have to take one of these type variables and replace it by two variables, or by one variable of sigma type, the obvious one. And so then this one, if we see that in a parameter list, we replace it by O, which is an O expression, and J, which is a judgment that O has type T. Mm-hmm. Oh, yeah. Yeah, so all the sub-expressions get translated by phi also. And so that's what you do. And then a verification of a proof, a verification of a proof is a derivation tree, and a derivation tree is once you encode all the inference rules, yeah, so let me show you how those inference rules are encoded. Let's go to the screen now. I'm going to the screen now. So there are the inference rules in Voevodsky's paper. And here are the inference rules in my program. The same ones, so you can just read them. And the program reads them. And at the moment, I don't really have a type checker for TS. I'm still working on my type checker at the LF level. This is parsed by my program. It's just the idea of 12, which is embedded here.
So you're writing a type checker for LF, and then inside of that is when they write the type checker for TS.
Yeah, exactly. And in fact, you could think of the type checker for TS as it being a tactic that's trying to convince the LF kernel that it has a derivation tree. And so you don't have to trust it, which seems to me might be an advantage from some sort of logical point of view. So I've got something like 30 plus rules in there so far. Oh, where's the beta reduction? Yeah, there's the beta reduction. You can see how beta reduction ends up looking. It's ever so much cleaner than it would otherwise have been in my naive way of thinking about it. So let me show you the code. Pardon me? I don't know. It just happened automatically. Oh, all right. It'll screw up, trust me. I don't know. I mean, I tried various sizes of, wait, it looks beautiful. What are you talking about? All right, so here's the top of the file that defines all the data types. And so, for example, we have constructors corresponding to the U expressions, T expressions, and O expressions that I've implemented so far. I've just done something like level TS0 and a few others from the paper. And then variables. And then something for tactics. And then LF expression head at the bottom there. The head of an LF expression, by that I mean these this H right here. That's the head of an LF expression. And these are the various possibilities. There are those constants of type U, T, and O that I just described. And then there are the variables. And then, oh yeah, this has the whole definition of all of the LF expressions in it. So the phi, that's the embedding I was just talking about. And so if we have a TS expression, phi of it will be an LF expression. And no code has to run. The data type, it's just an embedding of data types. So there's no actual work to doing the conversion. The parser takes a TS expression and makes an LF expression except for the phi wrapping around it. And then there's the lambda expression of LF. And then here, these three things have to do with pairs. And then marked, it just means marked with position from source code. Pardon me? There are two ways to do it. I could collapse these two types into one type and erase the phi. There'd be nothing wrong with that. But I decided to just keep them separate and have phi be explicit, just to prevent certain pattern matchings from succeeding, and so that certain functions would have different types. If, for example, a function was expecting an expression of TS, then it would be very likely to get one, because it would be declared to be expecting a TS expression rather than an LF expression. You could do it the other way around. You would just have a few more cases in your pattern matching that would have to fail if you were expecting a TS expression and not wanting an LF expression.
So except for the projections there, it looks like the TS expressions are kind of the neutral terms of LF, right? If we look at it.
Well, the words that I got from your paper are atomic and canonical.
Yes.
And I never can keep track of which one is which. But the canonical terms are these ones, and the atomic ones are these ones here. What would not be there? Oh, PR1 and PR2? Where should I put them?
As fair TS expression, just like a
Oh, they should be here? Yeah, I puzzled about where to put them.
Yeah, we can talk about that.
All right, you tell me why you think so. Yeah, that was a choice I made yesterday. So I didn't really much have a feeling for which place it should go, except I was pretty sure that I didn't want routines that were expecting a TS expression to get one of these. A routine expecting a TS expression, really, it can only get one of these applications. Because all of the TS expressions, as I described, Voevodsky says what a TS expression is. It's got one of these labels, and it's got some branches, and they're either O's or T's. And so it's not one of these things. And so that's why I put it here instead of there. Yeah, this is OCaml code. Yeah. So then the type family heads are these ones. There are a few more judgments having to do with universe levels and so on. You mean here? Oh, well, that's so that's so the parser knows that that's so I can generate a list of pairs, this thing and a string, and then the parser can look up the string and get the thing.
So why are these things here?
Oh, they're in another file. I thought that'd be too confusing for y'all. I can show you that file too. But a couple of days ago, I just went through and stripped all the strings out and put them into another file.
Show me the file, because you're duplicating information.
I don't know.
Setting yourself up.
So there are the strings.
You're duplicating information.
Yeah. Well, tell me later how to unduplicate, because I'm eager not to. And all right, so here are the first three type family constants: UX, PX, and OX, formed from those guys. And then here are some helper functions that form type families for me. And then here are some definitions of things that are useful in the later definitions, like here, for example, I wanted to abbreviate this thing with a name. So I gave it the name TEXP1. And then here are the definitions of all of those object level constants in LF. In addition to the ones that I wrote down on this board, these are just 3 of those. And oh, and then this thing is used for parsing. I have to parse expressions written in Vygotsky style. So this says that, for example, if the head is IP sub r, then the number of bound variables is 5, and bound variable number 0 binds this sub-expression, and that sub-expression.
What's the difference between the arrow and the same arrow?
The @arrow was defined above to be my particular constructor for these type families. Whoops.
Plain arrow is just OCaml over a case, right?
So there's the @arrow defined. It makes the crucial thing about the @arrow is that it makes a family level pi in LF from the 2 things. And then here come the kinds. So there's the basic kind and the pi kinds. And then, and then here comes the declaration of the kinds of those constants representing the various judgments that I advertised. And, and then we pass to contexts. And at the moment, a context is just a list of pairs, a variable together with its type in LF.
There's extra ones here, U-level equality,
Yeah, if you look at, there are a lot of things having to do with U-level. So for example, in the Tarski style of universe, there are these transition functions, J, that go from universe level number 1 to universe level number 2. And you know, if you want to compose that with another J, then the source of one better match the target of the other. And so as a premise of the inference rule that says you're allowed to compose these things is appearing the judgment that this one is equivalent to that one, at least on the space of solutions satisfying the list accumulated so far of universe level constraints. And so that's what U-level equality is all about. And then these other ones, the last 2, type U equality and object U equality, there's this another relation in his inference rules where the premises involve comparing 2 types or comparing 2 objects and looking at all of the U levels inside all of the essential terms inside of there to see whether they're all equivalent. And that's it. That defines the basic type structure. And then the, here's the file of inference rules. It's called rules.ts.
So you're using, you essentially implemented the part of the LF signature for describing the syntax directly in OCaml.
Yeah, it's constant. You know, this program is only going to do TS. It's not going to be 12.
Right. But then like the inference rules are.
But the inference rules are not constants.
Right.
The inference rules are in a file, and I thought that was really important because, first of all, I wanted humans to be able to read them, and that those @ arrows and so on that I'm forced to use inside OCaml are pretty disgusting. And this is the thing the human will really want to read.
But you might want to change the syntax.
Change it to what? Pardon me?
Maybe Vladimir wants to change his mind.
Well, I don't know how to encode the inference rules in his way. This is the only way I know how to encode the inference rules, right? Is that what you mean? These are not terms of TS. So
So, and just a question, like, I don't really understand why didn't you just use 12?
I want to write a proof assistant.
You can write a proof assistant and then use 12 to check the error. I mean, is this 12 would be the checker part of the proof assistant?
Yeah. Well, okay, but
I mean, if you want to write a proof assistant, then you're going to be writing code. But just, I mean, was this?
I think there's a lot in 12th that I don't need, like all of this adequacy theorem proving stuff. And what I wrote that does what you've seen so far, that's just 400 lines. So I don't really see the advantage of importing something like 12 when all I have to do is write 400 lines of code. And not only that, writing that code and debugging that code is preparing me for the next step, which is writing the TS type checker. I don't really, I need to understand these algorithms, and I'm a novice at all of this.
Okay, but on the other hand, you might then write a more general LF parser and checker, just not building in the OX.
Oh yeah, yes, that could be done in a day. But I have no need for that at the moment. Because if someone wants to modify TS slightly, change the source code of the program. It's one line of modification. And there's so few lines that define the few constants. There are just a dozen or two constants. It's the inference rules that are copious and large. And I think that's what's more important to be human readable.
I mean, but there's, if you want to play with patterns, you could play with different
With other type systems.
with the way that you
Yeah.
present the fact theory.
Yeah. Yeah, actually, it's a good point. Also, putting those constants into a file would mean that they could have source code positions decorating the decorating the objects, and then I could print out error messages that refer to those things. But anyway, I made this little file for a demo here. I don't really have user interaction per se. But, whoops. Dang. Oh, I see, there's some, dang. Yeah, I almost tried to or something, yeah, that's confusing. Where's my demo file? Demo, all right. Run it. Okay, it ran. All right, let's take a look at what happened here. So, oh yeah, this is another revelation about LF. You know, I was not just puzzling about where to put the inference rules, I was also puzzling about where to put the definitions. Because the definitions involve universe levels and types, and there are no lambdas for such things inside the TS. They only accept object level variables, not type variables and universe variables. And so LF also turned out to be the perfect repository for definitions. So here what we see is we're defining A to accept one universe level, and then we're defining T to be an instance of type capital U of little u, which means the universe corresponding to that universe level. And then we're taking EL of T. And that's supposed to be the type corresponding to that name of that universe. And oh, that's just showing that you can put, inequalities here. So, oh yeah, I didn't write it anywhere. But another thing you can do is Blavatsky envisions that the user will be able to type equations and inequalities here, like that, and just put them in there. And so those will appear as a prerequisite for the use of the definition. And so there's an example of a prerequisite. U should be equal to U. I couldn't think of a more complicated one in one variable to make that would actually be true. Yeah, I'm about to explain that. So, well, first of all, the semicolon ends what you would usually see in Coq. And then to the right of the semicolon is the LF term that justifies the judgment that the thing to the left of the semicolon is a type. And what we see down below where the thing ran is that it defined A at the LF level to be this lambda expression. So this little thing, that's the LF lambda. And, pardon? Well, okay, but now it's not. Things change. Adapt to change. Yeah, you can also type that in and it'll read it, as you saw on the other screen. So remember, oh yeah, so anyway, there are 4 variables, and then it, oh yeah, so I put in sigma types yesterday, and so now the definition returns a pair consisting of a type, EL of T, and consisting of a judgment, I mean, a type of judgment. Well, a term demonstrating the judgment. So that, this term just got copied into there, this term got copied into there, and this is the pair. And so the first thing came from the user written in TS notation, and the second thing came from the user written in LF notation. And then there are these various variables. So you can look at the type of A to see what type those variables have. The lambdas inside LF aren't decorated with types. And so the first thing, the U is supposed to be a U expression. Then the U300 is supposed to be a verification that U is equal to U. And so my idea there is that I won't encode proofs like that in the type system, and Blavatsky didn't think that would be done either. And that would just be an appeal to the kernel to check it. And then T is supposed to be an O expression. And then the next thing is a dummy variable, H for having a type. It's just a dummy variable. H means it has something to do with having a type. And then it says that T has the appropriate type, as I advertised over there on the board where I was talking about translating judgments. And remember when I was talking about translating context and parameter lists, I was saying that one parameter in a TS level definition or context would have to get translated into 2 parameters in the LF level context. So here we have the pair that it got translated into, just as I advertised before. And then what's the return type? It's a sigma type parameterized by a variable which is supposed to be a T expression, and then so in other words, it's supposed to be a pair which is a T expression such that the thing is a type. And that's what such that you have a derivation of that. And then, oh, and all this other stuff is just debugging output to see that the tactics and the normalization worked and so on. But, all right, so now,
Can I
yeah,
ask, is it important that there it says $H$299?
yeah, let's do that as our first bit of the demo. Suppose we get rid of that and we put a blank in. So then we get an error message that takes us to that blank. It says hole found, number 0. Its type should be has type that. And then it shows us a bit of the context. And now the user who puts a blank there could I mean, probably in an interactive system something else would happen, but this isn't interactive. I just ran the compiler and I got the error messages out and the program is over.
So you really should be, in your definition, it seems like you should be naming judgment as P has type U, and then you don't have to guess the magic number.
Yeah, well, yeah, what should I name it? Something based on T, maybe.
Don't generate the name. The user should write the name.
Well, see, there's no place to write that name over here. You think there has to be? I was thinking that, I don't know, suggest to me later all possible ideas for syntax. But I'll welcome them, but at the moment I don't see a place to put it.
Well, we're in a little bit of an in-between place here. Is that right? This is supposed to be.
It's under development. Everything's changing every day,
Like,
if that's
this
what
is
you
the
mean.
file format for the checker, right?
This is the file for the, this is what the user might type.
Okay.
The user, well, no, but we don't want the user to have to type this.
Right.
Hopefully this would all be filled in by tactics.
Okay.
Unless the judgment was undecidable yet true,
Yeah.
you know, and it couldn't decide it. And then the user has to go in. And so I really haven't put in any automatic judgments because I wanted to see what the user might have to resort to in the worst cases right away. And anyway, putting that in involves checking types at the TS level. And I don't have any code for checking types at the TS level yet. So that is the next level. So now so I can't really do. So I just have to punt for the moment and enter some LF syntax there. And so what is this EL type? Maybe I should clarify. There's the rule for EL type. It says that it's a type family of 2 arguments. It takes a universe level and it takes an O expression. And under the condition that O has that type, then EL of O is a type. That's the judgment. And so if we, in fact, what if we put an underscore for the whole thing? Then it takes us to the whole and it says, you want to justify the statement that EL of T is a type. And so then you look in your rule database and you see that you might do that with EL type. And then you get an error message that says it expected something to match that. In other words, the thing I typed, EL type, it has to take first, it's of type which is displayed there. It takes an argument M and an argument O and another argument, and then it will give you the judgment. So we have to give it 3 arguments. That's what we discern from that. And so let's put in 3 holes, and you know, maybe later on there'll be some sort of trivial tactic that puts in those 3 holes for me, but at the moment there isn't. And
By the way, why did the index get generated? Why is it 299?
well, just count. I just took your suggestion, and when gen-simming a variable, I just increment a counter, and so there were 298 times that had been done before it got to that point in the code.
I'm doing what? Reading in some library or what?
Oh, well, I'm gen-simming very often. Well, we read in the rule database, you know, and we type-checked it. And there was a lot of, unfortunately, when reading in the rules database, it was also expecting maybe there would be tactics in the rule database, and so it was gen-simming a lot.
So this means that if you have some development and then somebody changes a line
No one's ever going to type that $299. That would be totally ridiculous, because if you change one line of code, it would be ridiculous. You saw how I hope you didn't think I was proposing that the user would remember $299 and enshrine that in his code. No. But anyway, look, it says here we have a hole found, and we need to have a U expression. So now, you know, what I had in that spot originally was just U, which is the thing there. But I have a tactic. It's called assumption. I abbreviate it with $A, and it goes and it puts the U in. And it moves on to the next hole. Let's see where it put the U in. It should be on the screen somewhere. Oh, no, it's not on the screen anywhere because we're still going through the arguments there. But anyway, it put something in. We can be confident of that. And now it's asking for an O expression. And, well, you know, we see the context here. There's one thing that's an O expression. It's the T, and it's what we want for our inference rule. So let's just use the assumption tactic to get it. Oops, there's an underscore, a spurious underscore. And now we move on to the third hole. And now finally we get to, we have to demonstrate to our inference rule that T has that type. And now, by golly, you look in the context and there is a variable saying that it has that type. Now the previous time I wrote $299. So there are two things I could write at this time. I could write $0, meaning take the first variable in the context. And then the file finishes and everything's okay. And you can even see that the definition worked out, and it filled in H299 for me. That's a De Bruijn index, that's right. It's an index.
Did you do $?
All right, because your context is
Could I do what?
$A again?
You mean go back and put an underscore here or what?
So $A, and now $A.
Oh yeah, $A also works. Ta-da.
Why for the second $A, right? Like it could have.
This could always choose the wrong one.
Yeah, right. Just
Yeah. Yeah. So this is the first stupid tactic. It uses, and actually it's not just structural comparison though. It will unfold definitions as it goes up the context looking for types of the appropriate sort. Yeah, and then it takes the first one it finds. And anyway, you could imagine having lots of fun making a less trivial tactic and putting it there, but there aren't any yet. And I expect to have lots of fun doing that. And then, well, there are some other examples I was going to show to you. And this one at the bottom, define E, this is one I was working on this morning. And making it work, you know, by doing the procedure you just saw me do, where I type one hole at a time and see what's supposed to go in there. So at a certain point, it told me my hole had to be a function. And so I just made a function, hole maps to hole. And it told me what the second hole had to have as its type. And then I just thought, you know, eventually $A worked. And anyway, while I was doing this morning, I got 2 bugs found. And so I had to fix them. That's why I didn't have time to get all the way to the period.
I find it really interesting that this syntax where you have, you're giving a term in some sort of vague, explicit sense, but on this sort of, in part of that term, you're allowed to specify a particular tactic. I don't know, are there other precedents for this, or is this something new?
Yeah, to me it seems natural. I have,
The tactic is for type checking the term. Right? The tactic is for type checking the term.
I thought what we were saying is that you didn't have to specify what argument should go to LF. You just said,
Yeah, right. But like everything to the right of the semicolon is the typing derivation for the term that you just shortened.
but I think what he's saying is this is a tactic.
Tactics in the place of the hole.
Yeah, so this was my idea. I like the idea of having the tactic in the hole where it goes. Nothing else looks lexically scoped correctly to my eye. That's why I put it there.
So to the extent that
but no, it's not, because in AGDA, the tactic happens while you're writing this thing, but then once the code is done, the actual term gets put in there. Here, what
the
you
term
see,
could be something like reflect on the goal, apply some position, and search the context. I mean,
that's a term which has meaning inside the AGDA language, the reflection function.
Here's the code for the assumption tactic, if anyone wants to see it.
But yeah, but you can't. Yeah, but exactly. Yeah, the concept. Like in this one, we should just say what tech you want.
Why not? Say underscore and then the next line, you have a whole subgoal where you can use any set of tactics.
Right.
To refine else at blank, 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 and then underneath that, not be refined.
The different things right in the tactics inside the right.
Yeah.
You can use different things to achieve the same result. I'm just saying this is a syntax. You see here.
Well, not yet. I was thinking that they could also implement this tactic language of Coq with the semicolons and the brackets and the bars and things. And that might be sort of fun to do. It seems to me you could put anything inside there. One thing I haven't thought about, though, is it should be careful about capture of variables. If it returns a term that it got from outside, someone has to be careful. I suppose Coq is somehow handling that, too. Mm-hmm.
Are we in the end implementing the same system of marking up type theory, or is it logically a different system? And is it very impossible to say what not so much choose from a logical system?
Yeah, I have no idea what the other system is, so I'll let Per answer.
So like,
Rules or structures in the
yeah,
system.
like
Can you describe
to my understanding, like the major differences are there's Vladimir system for universes, which has very explicit coercions between each universe level and things like that.
Yeah.
Like it's not exactly anything we've exit before. And also some definitional data rules for numbers and for products and things like that. The source of the undecided variable.
Yes, because the system is being implemented here presented usually would be as a logical system, and you could study it and compare it with logical.
Yeah, I mean this is like on the wiki, right? Like this is the universe polymorphic type system.
Yeah.
Like all of these rules are described in inverse row format.
Here are two rules that make it undecidable. If there's a contradiction, things are equal.
Can different names name the same type?
What does it, you mean,
Yes.
do you mean?
Obviously, yes. Okay. So I think what I don't know if this is a difference than anything, but I think a distinguishing feature is that here types just stand by themselves. They are not elements of universes because we have taxon style universes. So you can think of this as having a bunch of types, and then the universes are kind of an afterthought. You can notice that types are universes, but you probably have to prove that every type in some universes that's even true. For example, if you have type variables, you can have type variables.
Not in the type theory TS, just in these definitions at the LF level. That's, yeah, in fact, the name of the rule indicates that. Yeah.
Basic difference is also my kind of type theory is based on the Gensen derived introduction whereas Vladimir wrote as such with a category derived formulation as a universal category.
computer.
So it's an untypable type system, but still the type type, if I understand it correctly, behaves exactly as other type types could be. So is TS not going to use any normalization at all during type checking? Because you could, even if the full type system isn't normalizing, one could potentially make normalization work here and there, you know.
Yeah.
For the efficiency of the
Yeah,
process.
so my plan is, I should have said that the algorithm for type checking that I implemented comes from the paper of Harper and Stone a few years ago. It depends in a crucial way on singleton types and subtyping, which I implemented at the LF level. And it's a very nice interlocking sequence of various bidirectional algorithms for checking equality of types, equality of terms, finding out what the type of a term is, and checking whether a term has a given type. And they were very careful in the description of their algorithm, and I followed that very closely in putting the algorithm in. And so my initial plan is to just take that algorithm after I get some experience with it, playing around with tactics and so on, and just put it in at the TS level. Now, things aren't decidable there, which means that it'll fail more often than the user would have liked. But Voivodsky has mentioned in his preprint already some subset of the definitional equalities that he regards as reductions. And he went to a lot of work to prove that various pairs of them are locally confluent, so that conceivably one could decide which reductions to do first, and quite often, from the user's point of view, get the equality that the user had in mind. And then when it fails, presumably the user had something else in mind, and the user would have to say so somehow. Maybe, I don't know exactly. This is an unknown to me. It's unknown territory. And so that's what will happen at the TS level. The other wrinkle, writing the type check at the TS level, is that instead of just returning an error message when it didn't work and returning nothing when it does work, I have to return their derivation tree that incorporates references to the rules database by name. So that's, I don't know how I'm going to do that at all yet either. Voivodsky's vision is that there will be rather few places where you have to do something that the computer couldn't figure out. And so probably you have your two types you're trying to show are equal, and the computer will reduce them to something, and usually they'll be equal, but if not, maybe the user will mention something, will announce an equality of some unrelated types, and the type checker will reduce those two, and they'll magically turn out to be the reduced forms you got, and so on. And so maybe you'll maybe the computer will have to string together a chain of 2 or 3 of these that the user provides.
So just say that this is what I had in mind, like, you might want to say a type system, or is it present a type system? Like these kinds of systems, like bidirectional type checking is something that you can express itself at the in terms of an LF solution.
Oh, show me that. Is that well known to people?
Yes.
Oh, well, show me that. I can always learn more.
Just a covert plan to get it.
Or to add code to it.
Is there any reason to think that this new type theory will have the same homotopical or consequential semantics that the conventional argument type theory has?
It was designed to have that.
There's an intention to capture it, right?
Oh. Well, Voivodski's pretty careful with his work that he writes down. On the other hand, he says this paper isn't complete, and you shouldn't regard anything above level TS0 as being the final word in the paper. So, but I gather the way he's designed the type system is just by very carefully thinking about the semantic model every step of the way. And every single definitional equality he writes down is actually true in the model. He wouldn't write it down otherwise.
So, since
Oh, well, I have no idea what the difference is. Sorry. Does it
I mean, you've got this free flying, I mean, there's a little bit missing, right?
No, because like you're making LF pies, your definitions are LF abstractions over universe levels, which can then be instantiated with particular ones. Like there's no universe inference with definitions. But
No, I don't see how it instantiates
Yeah, but
universes.
you get a bunch of many levels.
yeah, quantify over levels and then instantiate them through some other levels too.
The whole type system is parameterized by a single family of
Definition,
universe variables.
each definition gets an LF context with universe level variables.
Yeah, but my code doesn't.
That's a change that Dan makes, right?
No, but yeah, that's the point. My code does not incorporate a global family fixed for all time of equations. And in fact, I haven't quite decided what to do. But
But Vladimir tells it that way, right?
I mean,
Understand correctly. He says at the beginning, let us fix some universes and equations and then proceed from there.
all right, so I do it slightly differently. So here I have a command called check universes. Let's put the end of the file here. The universes are okay. Okay, let's make them not okay. Okay, they're not okay. No, wait, they are okay. No, that wasn't. No, that was the wrong one to change. I have to change.
U1, just change U2 to U1.
Oh, next of you. Oh, that should have actually failed.
It's not the same. Just change U2 to 1.
Oh, one error encountered. Oh, it didn't. Oh, there we go. That's a nice error message. Universe inconsistency. So what happened here was, what check universes command does is it gets the context and it scans the context for variables that are declared to justify some universe level equation or inequality. And it checks them. And the checking is very naive. There are 3 universe at this stage. I don't have any smart stuff in there, but what happens is that it plugs in 0 for U0, 10 for U1, and 20 for U2, and sees whether it's okay. And what?
It's a sound but incomplete algorithm.
Well, you know, it might be complete for all practical purposes. I'm hoping. I'm hoping that it's totally complete. Because after all, we can parameterize on all the universes. So, and Blavatsky keeps saying we only need 3, and here are the 3. So I might be done with this part of the program. There's nothing in the code for making new universe variables, except as parameters to definitions. And, you know, the inequalities will be there. And so, you know, the user will, the user might be able to deal with this universe checker. Yeah, and not only that, but to judgments that check the universe inequality that was stated in the list of parameters. So when the definition is applied, it'll be checked.
You seem to have made a lot of progress. There seems to be a number of people here who understand what you're doing here, could contribute. Are you ready to have other people join you with working on this and have a weekly working group or something like that to talk about what you're doing?
Ask me again in January. Right now, there are too many bugs and everything changes every day. But yeah, I don't know how long it'll feel like a one-person job. I just can't tell.
Is that a Chinese accent?
Yeah, that's ni hao. Means hello.
Is that your way of testing comparison?
The Unicode, just to make sure the Unicode works. In Macaulay 2, you can also use that as a variable name. Well, you want to be able to get your proofs checked in China, don't you? Not just in Brazil.
But they'll break, when they send them from China to Brazil, they'll break because in Brazil they don't have so many characters.
I don't know, you just wander around the streets of Rio and you'll see plenty. Thank you.